Example 1.17 is going to show us just how important the idea of domain is when discussing a function. It says here the following functions are defined without a domain specified. So I think there's a misconception out there that an equation, which is what I have here, f of x is 1 over x minus 4, misconception is that an equation is itself a function. But in reality, a function is more than just the equation. It is also the sets that are used along with the equation. So an equation is certainly an important part of the function, but it's not everything there is about the function. So if I was to give you just an equation like I have here, then I can ask you things like determine the largest possible domain of each function. So there's multiple parts to this. In this video, we're just looking at part A, and then it wants us to define each function using its domain and equation. So certainly a domain can be smaller than the largest possible, but oftentimes we are very interested in what the largest possible domain would be. So when we're thinking about domain, I want you to first think about all real numbers. Now, some functions will allow any real number to be substituted in for mapping, but not every real number can be used for all equations. Sometimes there are restrictions. So for example, on this one, we might try an integer like 1. So for example, f of 1. Well, if we plug in a 1, we'd have 1 over 1 minus 4, which would end up simplifying to be negative 1/3, which is a real number. So we're claiming that 1 maps to a real number. Now what that really means is that the value of 1 that we picked is going to be a part of the domain. But there's a lot of numbers that would actually work. For example, if I plugged in, I don't know, let's say negative 4, f of negative 4. So 1 divided by negative 4 minus 4, which is going to equal negative 1/8, which is also going to be an element of the real numbers. So we have all of these examples so far, both these examples giving us real number results, which means that each one of these numbers is part of the domain. So from a number line perspective, if I'm looking at the entire number line, oh, there's a lot of values that I would have to check. And there's certainly no way for me to go and check every single one of them. But if we start to understand the pattern that's created from the equation, then we might be able to more quickly get to an answer to this. So let me go ahead and mark negative 4 as well as positive 1, because we know that those values are going to be part of our domain. Now let me give you another value. I want you to try 4. And with 4, we're going to have 1 divided by 4 minus 4. And that's going to present a problem, because I'm going to then have 1 divided by 0. And 1 divided by 0 is an undefined operation. Division does not allow a denominator of 0 to occur. So that's not a real number, which means 4 is not going to be a part of my domain. So you can do this all day long, and you can pick a variety of real numbers. We've already done a positive and negative. You can do fractions, decimals, irrational, all kinds of stuff. And this value of 4 is going to be the only value that's going to give you this undefined result. It's going to be the only one. You can check all day long. Now, checking these things one at a time can be very tedious and time consuming. So there has to be a better way of being able to do that, and there is. Before I get to that, let me be sure to illustrate what the set is that we're talking about. So everything that's less than 4 and everything that's greater than 4 is going to be part of this domain. So again, the only number that we're not going to get to work with this is positive 4. So this takes us back to the beginning of the section where we started talking about infinite sets. So we can represent this infinite set. Everything to the left of the open circle is represented by negative infinity to 4. And then everything to the right of the open circle is 4 to infinity. And then we use that union operator to bring the two pieces together into one set. So we can say that the domain of f is equal to the set negative infinity to 4 union with the set 4 to infinity. And that gives us half of the question. We're being asked to describe what would be the largest possible domain for this function. So the equation helps us to see that, but we can also do this in an alternative way. If I take the expression that's in the denominator, which is x minus 4, and I set it equal to 0, and I solve this equation, that would tell me that x is equal to 4. And that is precisely the value that we saw giving us that undefined result. So there's a way to algebraically find exactly which number you want to keep out of your domain without having to go through this tedious checking of a variety of values. So this gives us an algebraic technique for doing that. So once you've established the domain, which we've now shown how to do that in two ways, you would then want to go and define the function using the domain and the equation. So when we're defining a function, we need to name the function. Now the name is already provided for us. The name is going to be f. Then I put a colon. And we always put the first set followed by the second set. The first set is what your domain represents. That's what was in a previous definition. So I'm going to copy down the domain and have that represent the first set. Now by definition, the domain is supposed to be all the numbers that will map to real numbers. So this is how we start our function definition, and this is given by, and we state the equation as the last piece, so that way we can reproduce the pattern using the values that we came up with for the domain. And that's the second part of this question, the defining of the function using the domain and equation.